All right, let's look at another example. We've got data, in this case 6 data points, taken from some specific mathematical function. What kind of function were these points taken from? From a linear function, an exponential function, a logarithmic function, or some other type of function that we haven't yet studied in depth. Let's get the data into our calculators. In the stat editor, you can see I've already got the data inputs, the x values in L1, the y values, the outputs in L2. I've checked and double checked my data entry, it's correct. So now I'm going to go to y equals, plot 1 is turned on, so let's hit zoom, stat, and we see from the scatter plot, well, I'm not sure what we're looking at there. I can't tell from, I can't tell here. The data looks at least approximately linear. So I'm actually not able to rule any of the options out from this graph. I don't know whether this data is increasing at a constant rate, at an increasing rate, at a decreasing rate, and so on. So my procedure is going to be to try each of the fits. I don't know whether this is linear from the graph. Let's see if it is. Stat, calc, and run a linear regression with inputs in L1, outputs in L2, and store the regression equation in Y1. Here's the linear model, the best linear fit to that data. Let's go to the graph. I'm going to look at the graph because I might be able to, well, that doesn't look exactly like an exact enough fit, but I'm not positive, so I'm going to go ahead and do the error analysis. The linear SSE, let's calculate the sum of the built-in residual list squared. Sum of squared errors is 5 times 10 to the minus 4, approximately. That's 0.0005. Small. Is it small enough? Let's calculate the average error. That's how we figure out whether this is close enough to conclude that we've got linear fit. The square root of that previous answer, the SSE, divided by the 6 data points. And that's 0.009. So the average error is 0.009. This data is not linear. 0.009 to 3 decimal places, that's 0.009, which is significant. It's non-zero to 3 decimal places, and I'm looking at 3 decimal place accuracy in my y values. These y values are presented to 3 decimal place accuracy. The average error of the linear fit is greater than that error. Okay? That's significant to 3 decimal places. So this is not linear. Let's see if it's exponential. Let's try that. Stat, calc, exponential regression with inputs in L1, with outputs in L2, and storing the regression equation in Y1. There's the exponential model that best fits the data. Let's look at the graph. Very similar. I'm not sure, so let's go ahead and calculate the SSE, the sum of the built-in residual list squared that is, so the exponential regression gives me, well, that's about 7 times 10 to the minus 4. That's actually a larger, that's more error than in the linear fit. This is not going to be exponential. I'll go ahead and calculate the average error, but I already know what the conclusion is. The square root, there's more error in this fit than in the linear fit. The square root of that SSE divided by 6, in y units, it's about 0.011. So again, that error is significant to 3 decimal places, and I'm testing data that's presented to 3 decimal place accuracy. So this is not exponential data. So let's try logarithmic. Stat, calc, LNREG, logarithmic regression, with inputs in L1, outputs in L2, storing the regression equation in Y1. There's the best fitting linear, the built-in residuals, the errors squared. The SSE is, so this is the logarithmic regression, the SSE is about 4, roughly, 4 times 10 to the minus 7. That's significantly smaller. That's 0.000004. The average error, to get us back to an error that we can compare directly to our y values, we use the average error, the square root of that SSE, previous answer, divided by the 6 data points, is about less than 3 times 10 to the minus 4, which is 0.0003 approximately. That average error is not significant to 3 decimal places. If I rounded that average error to 3 decimal places, I would get 0.000, which is not significant to 3 decimal place values given. And so my conclusion is that this data is logarithmic. Now, look what I did in these slides. There is another way, instead of mechanically trying each of the 3 possibilities, each of the 3 that we kind of have in play. What I did here was said, okay, from that original here, let's go back. So from the original scatter plot, I guess I need to hit zoom, stat. Oh, what's happening there? Stat, edit. Oh, right, I turned the plot off. Oops. Turn plot 1 on and hit zoom, stat. So here's where we were at the beginning. We saw that graph. We couldn't tell whether there was curvature here. So another way, another thing that I could have done instead of that mechanical process, which is fine, that's the way I chose to do it. But another thing I could have done is said, well, let's test directly for linearity by calculating the average rates of change. Because that actually can give us more information than either linear or not. The delta list L2, the change in outputs, divided by delta list L1, the corresponding change in inputs. We've gotten a lot quicker with these computations, haven't we? Delta list L2 divided by delta list L1. Those are the delta y over delta x values, the average rate of change on each of the intervals. From this set of average rates of change, we can see that on the interval from 25 to 26, we increased by 0.22 y units per x unit. And then we've got, clearly not a constant average rate of change. So here we can see quantitatively the nonlinear nature of the data. But we can also see that there's a trend in those average rates of change. The average rates of change are decreasing. Decreasing average rates of change means concave down. So if I had done this, I could have used this information to eliminate the linear and the exponential possibilities and just test for the logarithmic fit. So on these slides, I jumped right to checking the logarithmic fit and finding that that average error, as we already did, is not significant to 3 decimal place accuracy. And so we've got logarithmic. So there are different ways you can look at this, and there are different things that you might be able to do in order to save yourself some work. But one way or another, we've got a procedure that will let us determine the kind of function that data points came from.